Hello and welcome. I am Parsa Amini. I am a researcher at Alpen Wine Inc. Thank you for attending my talk. This talk is about providing you with a method for understanding allocators' impact on your program's runtime performance with regards to data locality, and it tries to demonstrate its role in long-running programs when you get diffuse allocations. That will be your takeaway from this talk. More specifically, we're going to talk about how we manage to quantify and explain the performance impact of select allocators for the purpose of publishing them in a book. The book I'm talking about is the book that is currently being written by Joshua Byrne and John Lakos at Bloomberg. It is titled C++ Allocators for the Working Programmer. And it is where you can learn everything about allocators. It would explain how allocators improve performance. It teaches how to write programs with CppCon. It explains what the benefits of local allocators are. And it's geared towards all levels of C++ programmers, all audience. Anyone writing C++ software would benefit from it. Now, the objective of our research for the material in this book, which is ongoing, is to provide empirical evidence and to quantify the benefits of using CppCon. We want to explain why the program runtime is affected and to show the underlying effect the allocator had on the hardware. Before this talk, some people reached out to me and asked whether some topics they were interested in were going to be covered in this talk, and some of it, unfortunately, is not going to be covered. So I made this slide to clarify what you won't see in this talk. I won't be covering allocator design. The allocators I use here are all already in the standard library. We are primarily concerned with x86 architecture. We're using Intel machines. If you're working on an AMD machine, if you have a PowerPC machine, ARM, M1 Mac, or anything else, you need to adjust a few things, maybe need different tools, but the rest of the talk is still useful to you. As for alternate memory types, you won't see any allocators do enable using them, but that's not the topic here today. As for the general purpose allocators, we use what the Linux operating system gives us as is, which means we're using the GNU allocator in glibc. As for concurrency, the programs you will see today do not have any concurrency. Everything is single-threaded. We're not using concurrency because it is easier to demonstrate the effect of preserving locality in a single-threaded program. The results are, of course, even more relevant to multi-threaded programs. Also, you will not see allocators that are used for instrumentation. Allocators are very useful for understanding program behavior. You can use them for testing, debugging, and profiling. That's not what we're focused on today because our goal is to analyze the performance of production allocators, not to provide debugging tools. Now that we know what is not covered here, let's move on to what is covered. Here's a list. We will analyze local memory allocator performance. We will measure performance. We will also see some diffuse allocations. And we'll see performance metrics, which we use, including execution time and hardware performance metrics. And we'll also show you how to simulate diffuse allocations. All the tools we use are already established. They're all existing tools. We're using Linux's perf tool. We're using Intel's vTune profiler. And for a library-based solution, we're using Project Perfmon2's libpfm for library. As we've said before, the question we want to focus on is how do we analyze the performance impact of allocators? So first, let's take a step back and talk about allocators themselves. As you all know, there are general-purpose global allocators, like the ones provided by GNU libc, the thread caching allocator, tcmalloc, Jason Evans's jmalloc, memalloc from Microsoft, and Horde. You use them with new and delete, or malloc free if you want to use the C API. Those are the interfaces you can access those implementations with. And there are also special purpose allocators like local, aka arena allocators, like the ones under the std_pmr namespace. General purpose global allocators are brilliant. They try to give you excellent performance in most use cases, but they're not what we're talking about here. We're talking about C++ allocators, local allocators. Local allocators provide runtime pluggable allocation strategies. You plug them in when you know their allocation strategy makes a difference to your code. Local allocators also provide special purpose memory resources, like std_pmr monotonic buffer resource, which allows allocating a lot of objects and then freeing them all at once you're done. And multiple allocators like std_pmr unsynchronized and synchronized pull resource. They don't work in all situations, but when they do, it's because they know more about how the allocated memory will be used than the global allocator would. So these allocators, which have special purposes, if you use them correctly, they improve performance. But why? How can they improve performance? One answer is that they can make allocation and deallocations faster. Why would allocation and deallocation take less time? Because if you know when and how much memory we need upfront, we can make fewer calls to neon delete. We can have a simpler allocation algorithm, like a monotonic incrementing allocator. Allocate, but only free once we're done. Do not free memory until we're done. We can also do no-op deallocations. That is, maybe we can skip calling the destructors, wink them out because we know that the object, we know what the object is, and we know that leaving it undestroyed is fine because it doesn't hold any memory except what was given to it by the parent allocator, and we can save time there. That is legal C++, and we are the ones in charge of the allocation, so there's no memory leak to worry about. The second answer is that allocators can improve locality. If we improve locality, we can reduce how much we wait on accessing memory. We can access fewer pages. If we access fewer pages, we get fewer page faults. If we improve locality, we can also get we can access fewer cache lines, so we get fewer cache misses. Consider, for example, the case of diffused allocations in a long-running program. Allocators can help you resist and protect against diffused allocations because they can give you better locality. And what do I mean by diffused allocations? Here's what I mean. Take this example. We create a std vector of std string, we reserve 4 elements, and then add 4 strings to it. When we print out the addresses of the memory allocated to the buffer inside the strings, we see that they are pretty close to each other. The 4 allocations stored addresses are exactly 32 bytes apart in our case. Yeah, 32 bytes apart. By the way, if you're wondering, yes, we did make sure that the strings you see here are large enough to avoid small buffer optimization. They're 17 characters, and plus the null terminator 18. And the threshold was 16 when I checked. So don't worry about small buffer optimizations. That's an example for a compact allocation that probably happens in the beginning of running a program. On the other hand, if you get a diffused allocation, then your allocations may be pretty far apart. They might be on different cache lines. They might be on different pages, which means accessing them could degrade your application's performance. In the first case, our 4 allocations were close to each other. This might be a luxury in a long-running program. Why? Because as the code keeps allocating and deallocating over a long period of time, the global heap becomes fragmented, which means at some point, calling new might give you diffused memory. What can you do about it? For one, you can reduce this degradation with a better choice of a general purpose global allocator. But that is orthogonal to our work. That is what you should do first. Then try to use allocators. Go use the best global allocator you can, and still the rest of what we can do with local allocators is relevant to you. What about local allocators? You can use a local allocator to protect against diffuse allocations. The global allocator, in contrast, doesn't know how you use memory. But you can use the local allocators when you know yourself and take advantage of it, because you know how small your task is. And by using a local allocator, you allocate a few large blocks and save time, and then you will not have diffusion. You will preserve data locality. So far, we explained how allocators can improve performance, which was in two ways: enabling faster allocations and better locality. Of these two, getting faster allocations is relevant when programs call allocate and deallocate too frequently. This is something we can easily measure with, say, putting a counter inside your program or with a profiler. The second one, on the other hand, getting better locality, is always important and also hard to measure. Now that we know how allocators can improve performance, how do we go about analyzing their impact on runtime? How do you do allocator performance analysis? What do you need to measure? What are the key performance metrics that we need to measure? Obviously, how fast the code runs is the most important. So execution time and metrics derived from it, like speed up, need to be measured. Another one is the number of page faults, which is reported by the operating system. It is an expensive operation, and we want to know if and how much it changes with use of allocators. We need hardware performance counters because we want to know how the memory system and, most importantly, caches get impacted by the use of allocators. Note that there's a lot more to this subject, and we only see what is relevant to our cases, which was more about locality. If you wish to characterize your software from the standpoint of allocators, you can refer to John Lakos' paper, P0089, revision 1. And there's also his Meeting C++ 2017 talk, and put the links up there for our online viewers would be able to watch them. In his talk, he identifies 5 dimensions that can be used for assessing allocators. He came up with the abbreviation devloc: density, variation, locality, utilization, and contention. We are simply focusing on locality here, mostly. Once we have performance metrics that we can measure, we can start collecting data. We don't do qualitative analysis. We want concrete and quantified analysis. We also want to consider that our results are intended to be published in a book, so we need to be concise and exhibit each relevant phenomenon in isolation. We also should take into account what is possible to measure on our machines. The list of, once we do that, the list of what performance metrics we can measure becomes execution time, how long does a program take to finish, how many page faults happen, and what does the different levels of cache events, event counts look like. How many cache accesses and misses, for instance, we have. So now what we need is an experiment. We need allocator implementations to compare. We need programs that showcase allocator usage. We need a benchmarking framework so we can measure performance, program's performance. We need an interface to access hardware performance counters. We need machines. I ordered these by importance, but I'll go through them in the opposite order because the less important ones, the bottom ones, take much less time to explain. These are the machines that we use for our experimenting. The first one, Milieu, is our primary performance measurement environment. We've specifically designated it for performance measurements. It's a quiet machine that gives us more precise measurements. And the graphs that you will soon see in this presentation are all results from runs on this machine. We also use 2 more machines for validation and debugging. The second one, Bug, is the workstation Joshua Byrne, who is responsible for most of the code in our experiment, develops and maintains our code. The third one, Marvin, is the machine. I previously did a lot of my exploratory research experiments when I was a student at LSU. And I owe special thanks to Dr. Harden Kaiser from the Louisiana Center for Computation Technology for allowing me to still access it. We have machines. We now need a benchmarking framework. We could use an existing benchmarking framework. I typically use Google Benchmark, but in this case, we didn't want an extra dependency, so we wrote a small one. The title of the book is C++ Allocators for the Working Programmer, CAWP. So the name we came up with is AWPBM, Allocators for the Working Programmer Benchmark System. The code conforms to the BDE coding style, which is what Bloomberg uses. BDE is Bloomberg Development Environments, or also known as Basic Development Environments, also known as BDE Development Environments, depends on who you ask. Like the other benchmarking frameworks, it runs your subject code in a loop. It has features to avoid interfering compiler optimizations and is able to read hardware performance counters through the use of libpfm library. This slide is to summarize what most developers need to know about performance counters. There's a counting mode, there's a sampling mode. In one, you count every event that happens through the lifetime of your program. And in the other, you sample, you read the counter's value every so often, which can be done periodically with the frequency or based on events. Another thing you need to know is that not every event you want is something you can measure. Your microarchitecture specifically must support it. Also, in case somebody is considering not using a software interface to access performance counters, and so you can shave off a dependency, then consider that directly accessing performance counter of your processor requires having, in case of x86 at least, you need privilege level 0. You cannot be in user mode. So you probably need to write a driver that does that for you. It's going to be fun for you to maintain it for all the architectures, microarchitectures, and platforms that you use. Might not be practical. Also note that reading performance counters requires a system call, like calling a read with a file descriptor. The point is that it's expensive and you can't do it very often because you're adding overhead, and every time you call it, every time you do it, you are distorting your own measurements. So if we don't want to come up with a software interface ourselves, what can we use that already exists for accessing performance counters? If you're using Linux, Linux has perf events API that you can use. It also provides the perf tool, which is a nice front end for the perf events API. We use the libpfm library and integrated it in our benchmarking framework because A, I'm more familiar with it, and B, it's because it's cross-platform. We're not aiming to just test on Linux. And C, it has better API, at least in my opinion. There's also Pappy. HPC developers love it. It's mature software from University of Tennessee at Knoxville, which is a cornerstone of HPC software research. And also note that Pappy uses libpfm underneath, but it provides a much nicer API. If you want something else, there's also Liquid, the Liquid project. It's brilliant software. I just don't use it myself. You can use any of these to read performance counter values. The difference between them is partially API, if you're wondering, but mostly about their various levels of support for different microarchitectures. They all try to provide better names for performance counters to make your code as the API user portable, so you can use the same code across architectures. But that's not always the case. That may not happen for the architecture you're on, sometimes because they haven't spent much time with that specific architectures. Sometimes your architecture doesn't expose counters for certain metrics that you want. And sometimes the libraries simply disagree reasonably about what performance counters are supposed to be measuring. Lastly, the VTune profiler. We are working on Intel machines, so we can also take advantage of the VTune profiler to access performance counters. If you know it's about VTune, it's been renamed to VTune profiler. It used to be VTune amplifier, and is now free under community support license for commercial projects. So if you have Intel hardware, you don't need to buy it anymore. You can use it. It used to be that you needed to pay for a license to use it. Now you pay for it if you want commercial support, if you need commercial support. The benefit and what makes it significant is that it's made by the vendor itself. So whatever Intel machine you are on, you can use it, and it provides a consistent experience across different Intel microarchitectures. You don't need to always fully understand every detail and change specific to your machine. One way it does, and one way it achieves that, is by giving you high-level composite metrics. Another benefit is that it nowadays provides a web interface, so you don't need to install the GUI or learn to use the command line effectively anymore. Also, if you do an analysis with the web interface, VTune is able to reproduce the command line, full command line that you would need to run the same experiment. So you can repeat that experiment, and that is very handy when you need to repeat that same experiment with different parameters. When I said VTune gives you high-level composite metrics, I'm talking about this. Consider the photo on the left. VTune is a profiler. You use it when you want to study the bottleneck for your applications. Is my application front-end bound? Is it back-end bound? If it is back-end bound, is it because I have memory accesses pending? What portion of instructions were stalled because of pending memory or cache accesses? It tells you those with higher level metrics. And another feature is, take the photo on the right, it also shows you a list of performance counter it uses when you run your program with it, which is, on your own, you can find you can find the full list of the performance counters your architecture supports on the vendor's website, say Intel, and try them out yourself. With VTune, you can see what those counters actually measure and try to understand if they're useful for your purposes. It uses a lot of counters, and you can see what they actually measure. VTune is a profiler, which means for us that you can, for instance, in this top-down tree, see what function was the hotspot for memory load and store operations. And you could also do the same for the most expensive, say, assembly instruction. This is a screenshot. If that blue band is distracting you, it's not important. So in summary, using VTune is good because it allows you to do a sanity check and to do a survey of what is possible to measure on your machine. Ideally, you know your application's code very well, at the assembly level especially. So you can verify your performance counter measurements and understand if they're possible, if they're correct, or you need adjustments. But maybe VTune can save you some time. The caveat is that VTune is a profiler, so it's not a replacement for everything else. You have the overhead of profiling in your measurements, and many measurements are sample values, which means your measurements are less accurate and precise than what you would do with if you just accessed plain counters and counted every event. That may be acceptable, but it may not be necessary or acceptable for you. But if you're having difficulty with measuring how memory-based code, how memory-bound your code is and where the hotspot for that metric is, where the most cache misses happen, that's where it helps you. Sampling is less accurate and precise than counting because not every event is counted. But some performance counters you want to use are only going to work in sampling mode. That depends on the architecture, obviously. They're very useful for profiling, but you can't count all events. Another caveat, I'm sorry, I forgot. This slide is about the issues you might be, the issues you will encounter when using performance counters. So the first one was that some counters only work in sampling mode, some only work in counting mode. Another one is that the counters do not provide uniform precision or accuracy. Depends on the counter and how the counter is implemented on the architecture itself. You need to understand what the counter actually measures. If you know what the counter measures on your machine and you want to work on a different microarchitecture, that counter with the same name might not measure the same thing anymore. You need to understand what it measures now. Another issue you might encounter is that if you're using Linux, for instance, you need to adjust the Unix kernel's panic mode, and that may not be possible to do in your environment. Not every counter you want to measure is available on the hardware you have. And another issue is performance counter overflows. Maybe your software handles it, but if you're doing it programmatically, you need to handle it yourself. If your counter overflows, you will not get accurate measurements. And lastly, we talk about different interfaces to access performance counter values. But one issue you will probably encounter with all of them is that not every counter that you know exists is known by its actual name, by the access interface, which means you have to refer to the manual, find out what the raw event ID is, provide that to the interface, get the value. In case of perf and on Intel hardware, you can use a wrapper like ocperf, which downloads the list of counters from the Intel website and enables you to use counter names. So you're less likely to make mistakes when translating event IDs. And with regards to not being able to use every counter you want because your hardware doesn't support it, one remedy that we used was that we took advantage of the fact that the clock speeds haven't really changed much since the aughts. And the memories are not significantly faster either, which means we can do our measurements, do our measurements on hardware that we know has the counters we want, and our results are more or less portable. Just use a different Intel architecture that you know has the counter. And if everything else fails, then in case of caches at least, there's one thing you can do. You can use a simulator, you can use cache grind. Your results are not going to be as accurate, but it helps you understand what your code does. Now, as for allocator implementations, we need 4 experiments. We use everything that's under, we use what's under std_pmr namespace. And the allocators under std_pmr allow choosing the allocation algorithm at runtime for the same code. That's what we're using it for. The baseline case is using it without an allocator, which is equivalent to std_pmr new delete resource. And the contender we're using is the monotonic buffer resource. The program we're using, it's a very simple program. It counts unique characters. You give it a string view, and it returns the number of unique characters in that string view. What's the variable for our experiment is the number of characters that were passed inside that string view. And we use different implementations of this function. We use one that uses a std set. I'm sorry, I need those other two are wrong. Std set and std set with a monotonic buffer, monotonic allocator, and the third one would be stud set with a monotonic allocator, but with a buffer. Oh, you forgot to update those last two. And we use these implementations with and without using a monotonic allocator. Yeah. This is the first code. This is the first example. This is the first code. It takes a stud string view. It instantiates a stud set of characters, inserts everything that's inside that string view, and returns the size. The stud set is supposed to do the actual counting for us. Very easy. The next one, we just use a monotonic buffer resource, pass and use, instead of using a stud set, we use a PMR set, which is just an alias that sets the actual allocator stud set is supposed to use. We pass that memory resource, everything else is the same. And lastly, we use a buffer and pass that. We create a buffer of 10,240 bytes. We came up with that number experimentally. And we use that buffer as the underlying memory for the monotonic buffer resource. And we make sure no other allocations happen by passing a null memory resource to the monotonic buffer. The rest of the code is the same, still using a stud set. So we have something to run. Now we move on to our results. The first thing we try to do is we try to understand how our data looks like. Get a survey how dispersed our data is, and this happens because we wanted to make sure that our error rates are acceptable for execution time. Then what you see in this graph is the comparison of the average durations of the three contending implementations. The y-axis shows the average duration of the iterations. The x-axis shows the size of this string view that was passed in to the function. And notice that the x-axis is logarithmic, base 2. We doubled the size of what we passed to the string view. And our contenders are listed over there. Stud set is just counting using a plain set. The second one uses a monotonic buffer resource. That label is incorrect. It's a stud set with a monotonic buffer resource. And the third one is also a stud set with a monotonic buffer resource and a local buffer. We repeated each experiment, our data collection 200 times, because we wanted to keep the range for the true value of all our duration measurements to be at least within 10% of the measurements within a confidence interval of 99%. You can call it an error rate of 10% if you want. And the way we came up with that number is we did 10 runs. We figured we estimated we need about 180 to keep the error rates keep the error within 10% for all values. We rounded it up to 200. That's why. The next thing we did is we took the averages of our data, plotted those, and added error bars. These are the averages. Our error bars measure the range within which the true value of each measurement is supposed to be within a confidence interval of 99%. And we see that our second contender, the stud set with a monotonic buffer resource, and the third contender, the stud set with a monotonic buffer resource and a local buffer, take less time to execute, and that using a buffer resource with a local allocator performs better. Remember, this is execution, this is duration, so less is better. To try to visualize what the difference is like, we took the previous graph, we normalized the results based on what stud set did, And we see that as the size of the stud string increases, both buffer resource and the stud set implemented, the second container and the third container, the ones with the monotonic buffer resource and the local buffer, tend to perform better, except the monotonic buffer, the stud set, the second container with a monotonic buffer resource, does initially perform worse when it tries to allocate because it's trying to initialize its own internal status, and that overtakes the actual time it has to spend on doing the counting the unit characters. And lastly, of the performance metrics that we looked at, we found that the number of actual memory loads we perform correlated the most with our results. We see that stud set performed the most number of loads, most number of memory accesses, and we see the same trend for monotonic buffer resource and monotonic buffer resource with a local buffer. That was a successful case. We managed to highlight the performance impact. We were able to compare the execution times. We were able to compare the containers' performance relative to the baseline to see how our containers improve upon the baseline case, stud set. And this visualization is effective and convincing. And we found the performance metric. In this case, it was number of memory accesses that explained the data best. Now, the second case we're going to investigate is going to involve diffused allocations. What we need to do is to simulate diffused allocations, which is what we call heap littering. The objective is to simulate the effect of a long-running program where you'd have a fragmented heap. And why? Because we want to show the impact of diffused allocations on our algorithm in long-running program. We saw how they perform initially, but what happens as our programs progress over time. If this was a tiny program we saw, but if this was happening in a long-running program, we might not have had such ideal conditions, and we might get worse data locality. Since we're doing it artificially, we now have an option, which is when we do the littering and how much littering to do. How do we perform littering is through this algorithm. We instrument new and delete. We run our program some number of times with delete disabled. So we allocate a lot. And we keep all those allocations in a static list, and then we randomly free a fraction, a configurable fraction of actual allocations randomly, and really randomly, and then start benchmarking as normal. And now we have a global heap that is fragmented to the extent that we wanted. Note that now that we have littering, it might affect our measurements because we are not interested in measuring littering, how the performing littering itself impacts performance. We need to exclude it. We need to exclude the littering stage from our measurements, and then we want to compare the algorithm performance with the litter heap against the baseline case, which didn't have any littering. Again, we are using the same code. We're using libpfm to access the performance counters. But if you wanted to do this experiment with perf and not do this not access performance counters programmatically, remember that you can start and stop perf measurements on command. Your program can send start and stop commands to perf with IPC. The caveat is that when you launch perf, you need to have those file descriptors, and your program also needs to know what those file descriptors are. So you write start, perf start, to measure, you stop. And if you want to do this in VTune, so you can compare it yourself, you can use the ITT pause and ITT resume functions, which are in the ITT notify header. And if that was too abstract in case of perf, this is a bash example just to show how it would show the concept of starting and stopping perf. You create we create two pipes, and we're using pipe because that's what we saw inside the perf's source code being accessed. And then we notice there's documentation for this. Then we launch perf. We say do not start any measurements with that delay equals -1. We pass dash control fd. We pass in the file descriptors for those pipes, run normally, and then here you should do this programmatically, but here just to show an example, I do sleep for inside the script itself. Your program would have the file descriptors, would do the next line, echo enable new line, send that to the file descriptors, perf would start measurements, and then send you an ack new line back, which you would read and then know that perf actually started, so you can go on and do the littering. We did that, and here is the littered case. Same code, count unique contenders. We're looking at the runtimes, and this is the littered case. How does this compare to the unlittered case, the original? We can see that the monotonic buffer resource, the contender 2 and contender 3, where we had PMR set with a monotonic buffer resource and the one with the local buffer, they are not really affected, but the original case is. So we have managed to protect against diffused allocations. We do the same relative comparison as we did before, except this time notice that the littering case, the littered case is, the littered cases are normalized to their own stud set measurements, and the unlittered ones are normalized to the unlittered case. And you can see that the monotonic buffer resource, the container, the PMR versions, when normalized, look like they are performing better. But that's only because the stud set implementation was impacted the most. We compared the number of memory loads as we did before, because last time it worked really well. And we compare it, we see that, as a matter of fact, the number of memory loads with littering for the stud set case has dropped. We're accessing fewer, we're accessing memory less often. And again, we compare the littered against unlittered case. We divided the runtimes. We see that spike at 2 to the power of 8 bytes. And we see that the stud set performed the worst over there. How does that look like for memory allocations? You see a drop, which means we allocated a lot less memory. We struggled to explain this for a while. And then we eventually found the explanation for it to be that the number of stalled instructions pending L1D loads. So we would not be accessing fewer memory locations. It's not that the front end is unable to issue instructions more frequently. It's just that the memory that we are trying to access because of diffusion is dispersed, and the act of accessing them just takes longer. We are unable to access memory as fast. Again, we managed to highlight the performance impact of local allocators on performance. We managed to compare the execution times, and we also provided effective visualization that summarized the main effect and identified the performance metric that explained how the littered case got impacted at the hardware level. So we got the results, we move on to conclusion. We show you how we got to choose the correct tool for every issue we had. We chose VTune. We had to use VTune for some exploratory understanding of what the hardware does. We had to use perf a lot because we needed in a Z frontend to run our code over and over. But we needed to provide accurate measurements at the library level. We had libpfm integration. We showed you how we worked around the resolution and precision constraints of the instrumentation and profiling tools. And we showed you how we designed effective presentation of visualization material. What is your takeaway from this talk? The main takeaway for you should be that this talk provided you with a method for understanding allocators' impact on your program's runtime performance. We showed you how data locality is impacted, which was a hard problem to measure, and counted for allocators' role in how allocators can impact your program's performance in long-running programs, where you get diffused allocations. And if you're not excited about this book, then you need to answer to John Likos over here. And but if you are excited and if you are willing to, you can volunteer to become a reviewer. We'll give you early drafts review. That ISBN is not going to work yet, but I'm assuming some people will try to access this talk online later. So if they search it, they'll show up by then. And this book is going to be out probably the third quarter next year, so look for an announcement early in the fall. And that is the end. If you have any questions, please fire away. Not yet, apparently.
How about now? Okay. So I expected that the runtime complexity of this algorithm would be at least linear, but from the results, it appeared as if it was faster than linear. Can you explain that?
No, we were not. I'm simply looking at it from the perspective of how this program's runtime gets impacted by what we're trying to measure. We are dealing with Stuxnet as it was, and the results should be easy to repeat on a machine.
Okay, thank you. Maybe will just explain my question. Like the algorithm was examining every character of the string, so I expected it to grow linearly with the length of the string, but it appeared that it was faster than that.
Every time it hits a duplicate, there's one less allocation it needs to do. So the longer the string, the more the duplicates start piling up, and you get fewer hits on the allocator.
Okay, thank you.
Oh yeah, we're not instantly adding unique elements all the time. Yes, some of them would be redundant, yes.
Hello. There are a couple of online questions, and I'll repeat them to you. This is a question from James Ballard. Can you please provide some more details on why you did not use an existing benchmark framework? So can you provide some more details on why you did not use an existing benchmark framework?
Because we just wanted one less dependency. You could use an existing benchmark framework. That's the only reason.
Okay. There is one more question. In your example, you beat std set in nearly every case. Have you seen similar results where you do not beat the standard allocators?
Sorry, I don't remember off the top of my head.
Okay. There is one last online question. What is the title of the book that you provided in the last few slides? We didn't see the title.
John Likos' talk, yeah. Local inside parentheses, arena memory allocators from meeting C++ 2017.
Okay, thank you.
That's what the one they want.
Okay. And I have a question myself. I saw that you are beating the performance of standard allocators using the monotonic buffer, but can you summarily explain what improvement is causing this, causing you to beat the performance of the standard allocator?
Local buffer that we are allocating.
Yeah, the
on
contender
on
2
the
and 3.
stack. So, it's when your program starts, the memory for it is already allocated, and the allocator doesn't need to actually call allocate. You're saving some time there.
Okay, thank you.